All right, welcome to Algebra 2, Target 23. This target focuses on how to use Euler's number, often just noted as E, in appropriate situations. So to begin with, let's talk about what E is and where it comes from. So one of the places where we see the value of E pop up is when we talk about compound interest. So in Target 22, you saw the compound interest formula, which is A equals P times 1 plus R over N to the N times T power. Okay, where P is the principal, the initial amount deposited, R is the interest rate, okay, for the annual interest rate, and then N is the number of times per year that it's compounded, okay, when T is the number of years. So what we want to do is consider an investment of $1 at 100% interest. Okay, so we're just to keep the numbers really simple. Okay, so that would make P equal to 1, would make R equal to 1, and then we're going to look at varying numbers of compounds over the course of 1 year. Okay, so we'll also use T is equal to 1. And we just want to see what happens as N changes. Right? So if we compound once per year, okay, so just by year, okay, then you'll end up, so if N is 1, then the amount at the end of that year would be equal to, right, because you're 100% interest, so you're basically doubling it. Now, if we increase that to compounding once per month, okay, so that now our formula is A equals 1 times 1 plus 1 divided by 12 to the 12th power. Okay, that gives us a value at the end of that year of 2.613. So a fair amount of increase just compounding by month instead of by year. Now, if we increase that to compounding every week, so there would be 52 compoundings, okay, the amount at the end of the year, okay, would be 2.6926. Okay, right, so about $2.69. Okay, increasing it to compounding every day, so that's 365 compounds, you end up with $2.71. If we increase that to compounding every hour, so we take 365 times 24, that's 8,762 or 60 compoundings, and that gives us an amount at the end of the year of $2.72 if we round it. Okay, so what we can see so far is that going from once per year to 12 times per year, we had a pretty significant jump. Okay, and then from 12 times to 52 times, there's not a very big jump. Okay? And as we go from 52 to 365, even a smaller jump. Okay? And from 365 to 8760, okay, even a smaller jump still. Okay? So you could probably expect if we compound by the minute, okay, which is 525,600 times per year, the amount at the end is still $2.72. Okay? So very small amount of change. Okay, from going out by the hour to by the minute, and if we increase again to the second, okay, which is what is that? 31,536,000 seconds in a year. If we compound it every second, okay, we still end up with $2.72. Okay, at the end of that year. Now, what we see is that okay, as we compound more and more times, okay, we end up getting closer and closer to this value, right? We ended up with, if we go to 4 decimal places, we ended up with the same value when we compounded by the minute and when we compounded by the second, this 2.7183. Well, we see this pattern, okay, in several different places, okay, including this one, and the first person who recognized that this number, okay, was being approached, okay, in several different situations was a guy named Leonard Euler. Okay, and he termed this to be the natural base. Okay, and it was named the letter E because Leonard Euler, is spelled E-U-L-E-R. So the E is just the first letter of his last name. So what this definition of E tells us is that as n approaches infinity, for 1 plus 1 over n to the nth power, which is basically what we were just working with, then E is approximately 2.718281828. Okay, and this is an irrational number, so it goes on forever, and there is no clear repetition in terms of what the numbers are. And this is what we call the natural base E. So what we've been working with is exponential models, where you have a to the b power. I'm sorry, let's change that to b to the a power. And then this b, what do we call that? We call that a base. Right? So we use e as a base in an exponential expression. That's why it's called the natural base. All right, so working with e is just like working with any other number, right? Because that's what e is. It's just a number. It's about 2.7. So when we work with e to powers, we work with it just like anything else to different powers. So if I have e to the second power times e to the fifth power, just like any other number, if I had x to the second power times x to the fifth power, right, we just add those exponents. So it's x to the 2 plus 5, or x to the 7th. Well, we do the same thing with e, right? This is just e to the 7th power. In the second example here, 12e to the 4th divided by 3e to the 3rd. Again, you just divide the numbers. 12 divided by 3 is 4, and we subtract the exponents, so subtract those, so it would be e to the first power, so it's just 4e. And again, if you have something to the first power, you don't need to write that first power. So we just end up with 4e. And negative exponents work the same way, right? We change it to a positive exponent and move it to the denominator. But first, let's use the power to a power rule. So we have 5 squared, and then e to the negative 6x. Multiplying those, and then we can change that to a positive exponent by moving it to the denominator. So 5 squared is 25, and then we can change it to a positive exponent by putting it in the denominator. So we have 25 over e to the 6x. All right. So simplifying expressions involving e is no different than simplifying expressions with exponents for any other number. Because again, that's all e is a number. Now, actually calculating e to a power, you're just going to use your calculator to do this. So if we take my calculator and calculate these values, where is e? Well, there's going to be 2 different buttons that have E on them. The first one that you're going to find is this button right here. The one that says ln on it. And you can see the second function of that is e to the x. So that's the button that we want to use. Right, especially if we're using powers. If we just want to use e to the first, then we wouldn't want to use this button. We'd just use the e button, which there is one, and it is right here, above the division key is the second function of that. All right, so if I want to calculate e to the 4th power, I just press second and then the ln button, and I get e to the power of 4. I enter that, and I get 54.598. If I want to do e to the negative 0.09 power, again, second, ln, and to the power of negative 0.09. And there I get 0.91. So now, again, something that we want to recognize is that when we take e to a positive power, okay, we're going to get a big number. Okay, when we take e to a negative power, just like with any other number, if you take e to a negative power, you get a small number, a fraction. Now, why is that important? Well, we've been talking about exponential growth and exponential decay. So in terms of e, a function of the form y equals a times e to the rx, okay, is called a natural base exponential function. So if r is greater than 0, okay, then the function is exponential growth, right? Which makes sense, because if you have e to a positive exponent, it's going to be greater than 1. Right? Because e to the r, okay, will be greater than 1 if r is greater than 0. And if r is less than 0, okay, then it will be exponential decay. Right? So what we're saying is e to the r is less than 1, okay, if r is less than 0. And that's how we determine if a natural base function is exponential growth or decay, just by the exponent. Okay, if the exponent is positive, it's going to be growth. If it's negative, it's going to be decay. All right, now for the biggest place that we use this is in compounded interest, and we use e when we continuously compound. Okay, so as we saw in the initial example, okay, as we compound more and more, we get closer and closer to this value of e. So basically, we use e if we're continuously compounding. So we're compounding every millisecond. Okay, so it's an infinite number of compounds. Okay, or just a really, really large number of compounds is continuously compounding. So the formula changes then to a equals p times e to the rt, where again, p is the principal, r is the annual interest rate, expressed as a decimal, and t is the time in years. So p times e to the rt. Sometimes we call this the PERT formula, because you have p, e, rt. So it's p times e to the rt exponent. All right, so some examples of using this. Okay, if we deposit $4,000 in the account, pays 6% annual interest, compounded continuously. Okay, so again, that's the word that we're looking for here that tells us we need to use e, the natural base. We want to know what's the balance after 1 year. So we have a equals p times e to the rt. Right, p is 4,000. Right, that's the initial investment. Okay, r is 6%, so 0.06, and we want after 1 year, so 1 year, so t is equal to 1. So substitute those values in, and you get a equals 4,000 times e to the 0.06 power. And if we calculate that, 4,000 times e to the 0.06 power. And we end up with $4,247.35. All right, so to summarize quickly, what is E? Okay, E is a number. That's what E is. Okay, about 2.7. Okay, and when do we use it? When we compound continuously. I think that's spelled wrong, but you get the idea. Okay, continuously. All right, so that is what E is and how we use it.